Welcome to Empowered Learning. This video will be the first of 3 videos to talk about solving first-order ordinary differential equations via substitution techniques. So specifically, what we're going to talk about in this video is how to deal with first-order ordinary differential equations that aren't directly integrable, they aren't separable, they're not autonomous, or they cannot be classified as a first order linear ODE in its general form. So whenever we're faced with first order ordinary differential equations that do not fall into any of the 4 categories I just described, then the next set of things that we want to do here is to see, is there some type of special substitution that we could use to be able to solve that first order ordinary differential equation. And the main idea behind each of these substitution techniques is to do a substitution so that we can go from whatever type of equation that we're going to solve here to get it back to something that we already know how to solve. Like we would want to do a substitution to either get it back to a directly integrable equation or separable equation, or something that's autonomous, which is a special case of a separable equation, or even a first order linear ordinary differential equation. So that is the main goal of this video series. So we're going to start off first about talking about the basics of solving first order ODEs via substitution. And then this video will conclude showing you about how to do linear substitution with examples. The second video in this series will go over what I call rational or fractional substitution. And this is just another way of saying we're dealing with homogeneous or homogeneous ODEs. And then the last video, I will go over the concept and examples of doing radical or a fractional exponent substitution. And those things are better known as Bernoulli equations. Okay, so for this first video, we'll be covering these first 2 topics here. For the second one, this next topic, and then the third one, this last topic. All right, so let's go ahead and dig in. So up to this point in your study of differential equations, especially if you're following my videos from the very first one I have up until now, you would have seen that we've studied equation solving techniques for the following types of equations. And of course, those are the ones I just mentioned. The directly integrable, separable, autonomous, which is a special case of separable, and first order linear. And so our goal now is to develop techniques that would help us to solve or help us to work with ODEs that would not be categorized as any of these equations above, but with a little help. And of course, that help is finding some clever substitution and algebraic manipulation techniques. We'll get these ODEs in a form that will either be separable or first order linear. Okay, so that is the main idea here. Now, for the basics, a first order ODE of this type, and when I say this type, I essentially just mean that we can rewrite the equation as dy over dx, and it's either equal to some function of x, function of y, or function of x and y. Okay, we know that if we have something that looks like this, then of course that function of x and y can be considered to be a composition of function of both x and y. And oftentimes we're not able to write functions, equations like those types of functions into a separable or linear first order ODE form directly. So note that since dy over dx is equal to a function that is composed of both x and y, and of course that's not equal to just a function of x, the case of being directly integrable or autonomous is not considered as a possible alternative for these equations. Okay, and I'm going to go back and show you that, because notice here that directly integrable is just a function of x, autonomous is just a function of y. So in other words, since the equations that we'll be dealing with here are not dy over dx is just equal to a function of one variable, then these 2 types of equations equation types for differential equations is not something that we're going to be able to get to directly. Okay. All right. So that is what I was trying to say in this particular sentence here. So in general, in order to use the techniques of solving ODEs that are not separable or linear via substitution, the key to using this method is to get creative with your substitution. In other words, we want to do a special type of substitution based upon a type of equation that will force that differential equation to go back to being either separable or first order linear. So that's the idea here, okay? And so that's what I say here in this next sentence. The goal of the creativity that you ideally would use to solve equations of this ilk would be to eventually end up with the ODE in another form that is more manageable to solve after the substitution is complete. And that is to say, our ODE turns out to be either separable or first order linear, okay? And I keep on stressing that first order linear because in differential equations, we do have second order linear and third order linear, and we deal with those types of equations differently than we do the first order. So that's one of the things that if you've noticed and you've watched my videos, I'm stressing for certain types of equation types. I'm always saying first order for that reason, okay? Unfortunately, there is no single bulletproof method or suggestion to do the substitution for all of the types of problems that we are going to, or all the types of the equations that we're going to study in this 3 video series. So we have special substitutions for each one. And so we'll study each one of those, but there's no one substitution that'll work for all 3. And that's the point that I'm trying to get across. So the first type of ODE that we're going to study that is of first order, but is not any of the 4 that I have mentioned earlier, will be a first order ODE where we can do linear substitution. And I'm calling this the linear substitution technique. Essentially, what we notice here is that we have a first order equation where we could rewrite it as dy over dx. And that's going to be equal to a function of this linear expression here. So somehow, somewhere in the definition of the ODE, we'll see that we have some inside function that looks linear in this characteristic. And so whenever we see that, what our substitution will be is to let u be whatever that linear expression is, okay? Now, once we figure out what we're going to let be our linear substitution in these instances, the goal at that point is to take that substitution and to be able to, number 1, solve for y, okay? And then after we solve for y, we'll also take the derivative of y with respect to x. And of course, you see y here. So we got dy over dx here, and somewhere in this, anything that we have in terms of y in this particular function here on the right-hand side of the equation, we need to be able to re-express that in terms of basically u and x. So that's the basic idea, okay? So for the steps, we want to verify that our ODE is not separable or linear in its current form. And reason why we want to do that, because if it's separable or linear, we'll just use separable or first order linear techniques to be able to solve that equation. Then next, we want to verify that it is of this type, okay? And then afterwards, if it is, then we let u equal this linear expression here. And then, of course, you see how we solve for y. And then afterwards, we take the derivative of y with respect to x for this particular expression here. And note that this derivative here is always going to come out to something that looks like this. So, of course, the thing we have to watch out for is what is a and what is b, okay? But it'll always end up looking like this. So after that's done, then we substitute the new representations for both y and derivative of y with respect to x into our original ODE up here. And then the resulting equation will be separable at that point. And then we use it solving separable ODE techniques. And if you've watched my previous videos on, or previous video on solving separable ODEs, then you know what to do there. All right, so let's look at our first example here. We first want to verify that the ODEs that we're dealing with will be a candidate for linear substitution. If it is, then we want to solve the ODE by using the suggested substitution that we just talked about. And then the final answer, we want to be able to write that explicitly as one variable in terms of the other. So basically like y in terms of x if we can, or x in terms of y, depending upon what we're given. All right, so for this first example here, we see that we have dy over dx is equal to tangent squared of x plus y. So as you've probably guessed, this is one that can do linear substitution here. And this x plus y is going to be what our substitution will be, because that is a linear expression that is stuffed on the inside of the function here on the right side. Okay. Now, in looking at this, as my note says here, note that there are no constant solutions because there's no one single value for y here that will make all of the right-hand side of this particular equation go to 0. Okay. So we don't have to worry about constant solutions for this particular problem. So here, as I said before, we're going to let u equal x plus y. And then from that, if we solve for y, then we'll get y is equal to u minus x, basically just subtracting x from both sides. And then we take the derivative of y with respect to x. Okay. So if we take the derivative of y with respect to x, then of course, notice here that when we do that, and I'm going to rewrite it here just to be clear. So if we take the derivative of y with respect to x, then this is like saying the derivative with respect to x of u minus x here. And of course, the derivative of u with respect to x would just be du over dx. And the derivative of x with respect to x would be minus 1. So that's how we get there. Okay. At times, we may have to, depending upon how this expression ends up looking, we may have to do the chain rule, but usually it's something simple like this. All right, so after that, we now have what dy over dx is in terms of x and u. We have what y is in terms of x and u. So we take that and we substitute it back into our original equation. Okay, so everywhere where we see y, and of course here we don't see it anywhere. Of course we see y here, but we have x plus y being covered by u. So that'll be taken care of there. The only thing here is dy over dx. So we just use the du over dx minus 1 for that. So once we are here, then what we're actually looking at is a separable equation. And so what we're going to do is do what we need to get it into a form so that we can easily solve. So if we look in here, add 1 to both sides, we recognize that tangent squared of u plus 1 is a trig identity, same as secant squared. And then of course, this particular equation is again separable, and you can easily see it here. So what we do now is just get everything in terms of u on one side, everything in terms of x on the other. And that's what you see me doing here. And of course, the reciprocal of secant squared is going to be cosine squared. And so that's why we have this on the left. Now, the most general antiderivative for 1 dx here is just going to be x plus some constant. Of course, here for cosine squared, it's not that easy to take the antiderivative of that directly, but we do have reduction formulas from trig that will say, hey, we can rewrite cosine squared in terms of something with cosine of 2u in it, okay? And so what I do here is I use the fact that cosine of 2u, one of its three trig identities, and so I use the one with cosine squared in it since that's what I need to replace. And of course, we just manipulate that around and we see that cosine squared is just the same as 1/2 of cosine of 2u plus 1, all in parentheses. And that is one of the reduction formulas from trig. So we replace cosine squared of u with 1/2 cosine of 2u plus 1. And of course, we can take the antiderivative of cosine of 2u relatively easy by using the substitution rule, and we get sine of 2u over 2. Antiderivative of u with respect to u, 1 with respect to u is just going to be u, and then plus the integration constant that I was talking about. So we take all this and we simplify everything, and the result here ends up being just 1/4 sine of 2u plus u, and then plus the constant. And please note that here that 1/2 only goes to these two terms here. It does not carry over to the value of c here. All right, so once that's done, then of course we have what the left-hand side of our original separable equation is. We can easily figure out the right side. So this is the result that we get from there. And then it's just a matter of substituting in what u was. So here we know that u here and u here was x plus y. So we go substitute that back in, do any simplifications that we need to, and we see that this is the final result. And of course, if I wanted to, I could rewrite this as y equals c minus all this business. But because this particular expression has y in it too, really doesn't profit me to solve for just y by itself, since y would be a function of itself, and that's technically not a function. So we're just going to leave it the way that it is. All right, so that is our first example. Let's go ahead and move on to the second. Okay, so for our next example here, we see that this is a function that can be expressed in this way as f of some linear expression here. So ax plus by plus c. And of course, I'm saying linear here because we know that ax plus by equals c is the general form of an equation of a line. So that's why I'm saying that. Now, of course, here would be what that linear expression that's on the inside of that composition function looks like here. So we're just going to say let u equal y minus x plus 5. And then afterwards, we'll find out what u is. Find out what y is, and find out what dy over dx is. Okay. So u is going to be y minus x plus 5. So if we solve for y, then y is going to be u plus x minus 5. Okay. And this implies that our dy over dx is just going to be, take the derivative of u with respect to x, take derivative of x with respect to x, and that's just 1, and take the derivative of any constant, and that's 0. So we just leave that as is. So now that we have all of that, we know that dy over dx equals 1 plus e raised to the y minus x plus 5. That is the same as saying du over dx plus 1 equals 1 plus e raised to the u. And so now from here, we see if we subtract 1 from both sides, these 1s will essentially cancel to 0. And what we have here is du over dx is equal to e raised to the u. And so at this point, you recognize that this is a separable equation, okay? So at this point, you know that it's separable because I could rearrange the way that this looks so that I have everything in terms of u on one side, everything in terms of x on the other. And so in doing that, see that that's the result of that. And I can just rewrite this as e raised to the negative u times du over dx. Okay, and so now from here, I can integrate both sides. And of course, e raised to the minus u du, if I take the antiderivative of that, would be minus e raised to the minus u. And on the left side, on the right side, we know that integral of 1 dx is just going to be x. Yeah, I can't write this u for some reason. So let me try it one more time. Nope. So here on the right side, we'll just have x plus constant. And so now from here, pretty much on easy street. So all we need to do now is really just solve this for u, and then substitute back in what u was. And actually, I'll go ahead and substitute what u was first. So here u was y minus x plus 5. This is x plus c. And then, of course, from here, I need to get this y minus x plus 5 out of the exponent of that. So what I can do is take the natural log of both sides. But before I do that, here, I'm going to go ahead and multiply both sides by a negative 1 here. So if I do that, this will be the situation here. It's be minus x minus c. And then from there, we'll go ahead and take the natural log of both sides. Now, of course, from there, everything that's in the exponent will be able to come out. It's going to be a minus y minus x plus 5. And I'm just keeping the minus out here because I'm hoping that eventually it will go away. And so natural log of e raised to all this is just going to be that on the left-hand side. On the right-hand side, I will just have this situation here. And so now what I need to do is just solve for y in this case. So to do that, I would need to distribute. So I'll have minus y plus x minus 5. That will be equal to natural log of minus x minus c. And of course, solve for y, I would just subtract x and add 5 to both sides. So I would have natural log of minus x minus c minus x plus 5. And so this would be the final answer here. So this would be considered our general solution to this ODE. And just so that we know, now that we actually know what the solution is, we also need to know what are going to be the valid or legal values of x we can plug into it. Since we have this expression of minus x minus c inside this logarithm, one of the things that we know is that whatever arguments we put inside a logarithm, they have to be non-negative. So in other words, x minus c has to be greater than 0. Okay? Or we could look at this another way, putting parentheses around this, saying that's x plus c times a negative 1 has to be greater than 0. So that means that x plus c would have to be a negative quantity. And so, of course, what this means here is that whatever c is, it will have to be less than whatever the x value is for that to work. Okay? Or we can say that x has to be less than negative c if you want to look at it that way. So probably the most convenient way to look at it is like this, where whatever constant we have, we know it's going to work only if that value is less than whatever x value it is that we're dealing with for a specific response to this particular function. All right, so let's move on to the next example. So this next example is a first order ODE that's going to be a candidate for linear substitution, but is also an initial value problem. So we're going to see how all that works together. So we have dy over dx is equal to some expression here that looks like a function of both x and y. And we see that here we could kind of look at this as something divided by something plus 2. So that lets us know that we could do our linear substitution where we let u equal 3x plus 2y plus 2. Okay. Now, since we know what u is, of course, the goal is to figure out what y will be and what dy over dx would be. So we look at this situation here, and we note that since we got something very similar in the numerator and denominator, that what's in the numerator here, since we have u is equal to 3x plus 2y plus 2, then we know if we subtract 2 from both sides that what the numerator is u minus 2. And of course we want that because we want everything here either in terms of u and or x. Okay. So here we see that the right hand side of this ODE is just u minus 2 over u. And this is just going to be a function of u. Thus, we can do we've already done our linear substitution. We just need to figure out what dy over dx is, okay, based upon that. So here we revisit the fact that u is equal to 3x plus 2y minus 2. Solve this for y. We see that's what this equals to. And then we take the derivative of y with respect to x. And of course, first term would just be 1/2 du over dx. Second term would just be minus 3 over 2. And third term, constants take derivative, always 0. So now we have a way to express dy over dx in terms of x and or u. And of course, the right-hand side is already expressed in terms of u. So our equation that we have here, we can now rewrite it in terms of just u and x. And we see that that's what that is. This, of course, was the right-hand side of the equation that we found earlier. This we found from up here, dy over dx. And so we just replaced dy over dx with that here. Now, at this point, what you're looking at is technically a separable equation. Okay? Doesn't quite look like it, but because of the substitutions that we did, We know it's going to either turn out to be separable or directly integrable, and all we have to do is just work it out to see. So as you can see in these next few steps, I go, this step I'm just multiplying both sides by 2 to get this. After that's done, I add 3 to both sides to get this step. And of course here I'm trying to clean up all this business on the right hand side here. So that's why you see the 2u minus 4, because I'm just multiplying 2 times the numerator there, all that over u. And then I know since this has to be u in the denominator, then I know that u over u here will allow me to be able to combine all this together, which ends up being 5u minus 4 over u. So all this that I'm talking about here just simplifies to du over dx is equal to 5u minus 4 all over u. And then at this point, it should be really easy to see how this is a separable ODE. So do some cross multiplying and such, and we see that our solution ends up being this. And we know that the goal here is to be able to integrate both sides. And of course, on the left-hand side, we could use substitution rule to be able to do that. So here we let w equal 5u minus 4, and then of course do the business that we need to be able to rewrite the left-hand side integrand here in terms of w. So we do that, and of course u times du over 5u minus 4. We can rewrite it as what you see here. So that means that, of course, I've rewritten it some more to make it a little bit easier to deal with whenever we actually have to take the antiderivative of this. And so I rewrite it in this form so that it's relatively easy to do. All right, so now to finish up, we have the left side and the right side of our equation now rewritten in terms of u and or x. And of course it's separable, everything with x on one side, everything with u on the other. And went ahead and replaced this with the 1 over 25 times 1 plus 4 times 1 divided by w. Finally integrate. We take the antiderivative of 1 with respect to w was w. 4 times antiderivative of 1 over w with respect to w is natural log of absolute value of w. And then from this point, we just go back substitute and solve for y. Back substitute here to get back u, and then back substitute again u to solve for y. Yeah. So we know that w was equal to u minus 4. So in place of w here and here, we write u minus 5u minus 4, 5u minus 4. And then once again, u was 3x plus 2y minus 2. So for everywhere where we had u, we replace it now with 3x plus 2y minus 2. Okay. And then of course from here is just a whole lot of algebraic manipulation to get it into a form that'll be easiest for us to deal with. And the general solution to this ODE will be at this line here that I've starred. And that's probably the easiest we're going to be able to get that to look. Okay. So now we apply our initial condition of when x is 1, when x is negative 1, y is negative 1 as well. And again, all we do is just substitute in those values. Let x be negative 1, let y be negative 1 as well, and solve for d. And we see that d ends up being something that's not too pretty, but nonetheless, that's what it is. So it ends up being 20 times natural log of 39 minus 2, which we can also rewrite as natural log of 39 raised to the 20 minus 2. Okay? And of course, our final answer ends up being this here, where our d just ends up being natural log of 39 raised to the 20 minus 2. Now, the last note that I make here is that since the derivative of y with respect to x equal to this 3x minus 2y over 3x plus 2y divided by 3x plus 2y plus 2. That tells us here that our denominator is not allowed to equal 0, okay? And so since our denominator is not allowed to equal 0, then what this also tells us, if I go solve for y, is that y can't be equal to negative 3/2 x minus 1. So what this means is that all combinations of x and y that are along the line of y is equal to negative 3/2 x minus 1 will not be a valid combination of x and y values that we can use in the solution that we've come up with here, okay? So if you want to think about what that looks like, that basically looks like you can choose any combination of x and y values in the xy plane that you want, but anything along that line you would have to throw out. So you would have basically an xy plane with a line through it where that line of points you can't use. All right, so let's move on to the next example. Okay, so for this next example, we do have another initial value problem here, but this problem is going to be a little different. And so one of the reasons why I picked it is because there are some spots in this particular problem that if we kind of do the math haphazardly, we may run into some trouble in that we may give ourselves a whole lot more work to do that may result in us making a mistake in our work. So I wanted to point one out like this just to make you aware of certain places in the process of doing this problem that you should pay attention. All right, so this one's another one that's already worked out, so I'll just kind of talk through it. So here we see that we have our ODE here, and I can rearrange this ODE to look like this. And of course, this looks like a function of composition function where the inside function is a linear expression. So we know that we can use lin sub here, linear substitution. So we identify that u, of course, is going to be the y minus 2x plus 3. Then, of course, we solve for y, adding 2x and subtracting 3 from both sides. Take the derivative of y with respect to x, and we get du over dx plus 2. Of course, all that should be relatively easy to pick up. So now that we have that, we have a way to be able to replace dy over dx, and we have a way to replace our linear expression here, so that everything now will either be in terms of u and or x. So the left-hand side, dy over dx, is the same as du over dx plus 2. Right-hand side is 2 plus square root of linear expression, so 2 plus square root of u. And then from this point, we should be able to recognize that, yes, this is going to be a separable type of equation. And if we look closer here, if we had to subtract 2 from both sides, then of course those 2's would cancel to 0, and all we would have left is du over dx is equal to square root of u. And of course, at this point, this is a separable ODE. So we get it to where everything with u on one side, everything with x on the other. See that this is the outcome, and then we integrate both sides. So in doing the integration, of course, we use the power rule for antiderivatives for the u raised to the negative 1/2. Then, of course, we're going to get 2u raised to the 1/2 equals. And, of course, the antiderivative of 1 with respect to x is just x. And then since both of these are indefinite integrals, we know that both of them have an integration constant, but for simplicity, we just put it on the right-hand side. And so with that, of course, u raised to the 1/2 is the same as square root of u, and u was our y minus 2x plus 3. So you see how we put that all back in. And so now I'm calling this our implicit general solution. And it's that because, of course, everything's written in terms of x and y. Okay. Now, one thing that you are not seeing me do here, and this is what I wanted to point out, is that I did not say, well, hey, let me try to solve this particular equation for y, and then apply the initial condition. I didn't do that. The reason I didn't do it, and I'm going to explain it more in detail on the next page, but anytime I have a square root on one side of an equation and it's the only term that's there, notice that in order to get to this y, I would have to square both sides, okay? And if I did that, that's fine. However, when I square both sides, notice that the squaring action or a squaring operation that I do does not know if this left-hand side here is either positive 2 times square root of all this business, or if it's negative 2 times square root of all this business. Doesn't know at all, okay? So because of that, and because of the fact that we're dealing with an initial condition here, we want to be very, very careful because we may be assuming something that isn't, okay, by jumping the gun here and trying to solve for y too early in this case. So that was the reason why I just said, hey, well, let's figure out what the integration constant is without having to do that. And then afterwards, we can figure out everything that we need to know if we have to consider signage later. Okay, so now at this point, we need to go ahead and apply our initial condition. So we do that when x is when x is -1, y is -1. So we just go ahead and plug all that information into our implicit general solution here. And we see that we end up getting that c is equal to 5. Okay, so we know what that is now. And at this point, we'll go ahead and try to figure out what y is, since we know what c actually is now. So we let c equals 5, go ahead and square both sides of this equation here. Of course, that's doing that. This is the result that we get. And then, of course, we can distribute our 4 across all 3 terms there, get this situation here. And at this point, we can go ahead and solve for y to be written explicitly in terms of x. And we see that this is our particular explicit solution. And I'm naming it that because of the fact we had an initial condition and we applied it and we found out that c was 5. Out of the family of solutions that we had up here, we know that the specific one that we wanted for when, I guess the initial condition of the point -1, -1 being on the graph is going to be this one, okay? And so last thing to note here is that we have no constant solutions for this particular ODE, and that's mainly because the square root of our linear expression here can't be -2. Now, why does that matter? Well, if we go back up to our original problem here, notice that this says dy over dx is equal to 2 plus square root of our linear expression here, okay? We know that we only have constant solutions whenever we have some value of y that makes our entire right side of this equation equal 0. And the only way this entire side of this equation here is going to equal 0 is if square root of y minus 2x plus 3, if all of that is -2. And that's virtually impossible because of the fact that we know anytime we take square root of something and we're dealing with equations, it has to be non-negative. And of course, this function I've drawn up here lets you know what your basic square root of x function looks like, and you see that it's non-negative. There's no way that this particular function is going to equal to a -2 for its y value. So there's no way that that's going to happen for this either. So that's why we have no constant solutions. All right, let's move on to the next example. So one more thing before we move to that next example. I told you I was going to give you a detailed reason why we didn't want to square both sides and solve for y first. And so I kind of go through this process here. So if we actually did try to solve for y first in this initial value problem, this is what it would look like. So of course you'll square both sides as normal and you'll get this. And then of course we'll apply the initial condition here. And notice that when we do that and we solve for c, what we end up getting for c as a result is 2 answers. Okay. And so what we would have to do in this instance, since we have 2 answers, is to figure out which one is actually correct. Now, of course, we know from doing the problem that the c equals 5 is the correct one. But notice that this process here gave us 2 answers. And that's mainly because going from this step to this step, if you write your math notation correctly, anytime we solve an equation like this, we have to take the principal root of both sides. Okay, which means over here we have to have plus or minus square root of whatever this is. And of course, on this side, it just has to be whatever the expression is that's being squared. Okay. So in order for us to figure out which one of these solutions is correct, if we had it like this, we would actually have to go back and plug it back in and see does it actually work. Okay. Now, of course, if I do that when c is equal to -3, then we'll have this equation here, plugging in when x is -1, y is -1, and c is equal to -3. We plug all that stuff in, and you see the result that we get here is this. Where we have 4 is equal to -4. And of course, 4 isn't equal to -4, so that's how we know that the c equals -3 is an extraneous solution. Again, my point is that there's nothing wrong with doing it this way, but look at all the extra work that we're doing, and we could have just avoided it by just not squaring both sides in the first place. Okay, so that is the point that I'm trying to get at here. Okay, all right, so now let's move to that next example. Okay, so this is our next and final example, and so we see here another initial value problem, where in this case we have dy over dx is equal to cosine of x plus y. Of course, this looks like it could be a lens sub candidate, and we're going to let u equal x plus y. Of course, that means if we solve for y, that's going to be u minus x, which implies that dy over dx is going to be du over dx minus 1 when we take the derivative of both u with respect to x and x with respect to x. So now that we have all that here, dy over dx is just du over dx minus 1. Cosine of x plus y is just cosine of u. And so now at this point, we know that we have a separable equation. May not necessarily be in the best form for it to be separable, but it is separable nonetheless. So we just need to rearrange everything to where everything in terms of u is on one side, everything in terms of x is on the other. So we'll start off here by adding 1 to both sides, so that we have du over dx is equal to cosine of u plus 1. Now, at this point, you would probably want to go ahead and get everything with u on one side, and we'll go ahead and do that. So we got du over cosine of u plus 1. And this will be equal to dx over here, okay? Now, if you're looking at this, you're like, yeah, great. I know I need to take the integral of both sides here, But you're looking at this and probably are saying, well, how do I take the integral of that? And that's a good question, okay? So here, the way that we're going to handle this is we know that we don't have a direct way to take the antiderivative of 1 divided by cosine of u plus 1 directly. But what we can do is utilize the fact of we can multiply the numerator and denominator of this expression by the conjugate of the denominator to give us something a little bit more familiar to us, okay? So my point here is that if I do cosine of u plus 1, and let's say I multiply it times cosine of u minus 1, then what this looks like to you is a minus b or a plus b times a minus b situation here, okay? And of course, a plus b times a minus b is a squared minus b squared. And if I know that I can rewrite this as cosine squared u minus 1, this looks like something that's a little bit more familiar that we can simplify, because this looks like the negative of one of those trig identities, okay? And specifically speaking, we know we have this situation here. And of course, all this would just be negative sine squared u. And that's something that we can deal with, okay? So what we're going to do here, now I'll erase this, but what we're going to do is multiply numerator and denominator of this left expression by the conjugate of the denominator and try to see what we come up with and see will that give us something that we can actually work with to be able to integrate relatively easy. All right, so let's take this left-hand side here for just a second. So let's say note that 1 over cosine of u plus 1 is equal to 1 over cosine of u plus 1. But now we're going to multiply both sides here by the conjugate of the denominator. And let's fix that. All right, so I was having some pen issues there, but I think I got it under control now. So this means that I'll have cosine of u minus 1 in the numerator. And of course, in the denominator here, remember how we said that cosine of u plus 1 times cosine of u minus 1, all that was going to be cosine squared of u minus 1. So I'll go ahead and write that. And remember how we said all of this equivalently was just a negative sine squared of u. Okay. So now from here, we see that I have cosine divided by a minus sine squared, a cosine minus 1 divided by a minus sine squared. I'm going to go ahead and move this minus sign up to the numerator so that now this looks like 1 minus cosine of u over sine squared u. And of course, if I split this up in two separate fractions, I'll have 1 divided by sine squared, which is the same as secant squared of u. And here I will have cosine divided by sine squared. That is the same as saying cosine of u over 1. I have sine squared, not sine. So this is going to be sine of u times 1 over sine of u. And essentially what I'm trying to get at here is that cosine over sine is cotangent, and 1 over sine is cosecant. So I'll have cosecant squared u here minus cotangent u times cosecant u. And so in dealing with this new expression here, this is a little easier for us to deal with because of the fact that if we look at cotangent u times cosecant u, we know what the antiderivative of that is, okay? And that's actually just going to be cosecant u. If we look at what cosecant squared is, remember that the derivative of cotangent is negative cosecant squared. So that means that the antiderivative of cosecant would be a negative cotangent. So we have something in we have this particular expression here, the 1 divided by cosine of u plus 1, in a form that will let us be able to integrate with relative ease. Okay, so because of that, we'll say that du over cosine of u plus 1, we'll go ahead and just say we want to integrate that. That's going to be the same as integrating cosecant squared of u minus cotangent u cosecant u. And of course that would be du, like that. And like I said before, the antiderivative of cosecant squared of u will be a minus cotangent, since the derivative of cotangent is minus cosecant squared. And then the antiderivative of cosecant, negative cosecant cotangent is just going to be a positive cosecant, and it'll be cosecant of u. So now that we have all that business here, then that means that this left-hand side here of our separable part of our equation, we take the antiderivative of it along with the right-hand side, and this is just going to be a negative cotangent u plus cosecant u, and on the right-hand side it'll be x plus c. So at this point, the hard part is over. Everything else is just a matter of us back substituting in what u was and then applying our initial conditions to figure out what c is, and then we'll be done. So at this point, let's go ahead and say this is our general solution. Oh, sorry, well, not general solution yet, because we still need to substitute back in what u was. So we'll backtrack on that for just a second. Yeah, and we'll wait until after we're actually done back substituting. All right. So here we just want to recall that u was going to be x plus y. So here we have, therefore, and I'm going to switch these two terms around just because I don't want to forget to write the negatives later on. So I'm going to say cosecant of u. I'm trying to back substitute u here. So cosecant of x plus y minus cotangent of x plus y, and that'll be equal to x plus c. And so from here, this would be our general solution. All right, and so now we need to apply our initial condition here. So the initial condition, when x is 0, y is pi over 4. And so here we have cosecant of 0 plus pi over 4, which is just pi over 4 here, minus cotangent of 0 plus pi over 4. And this would equal to x, which is 0, plus c, which would just be c. All right, so now at this point, all we need to do is evaluate cosecant of pi over 4 and cotangent pi over 4. If you don't recognize what this is right off the bat, that's fine. We'll go ahead and translate this into things that look a little bit more familiar. So cosecant is the same as 1 over sine. So we got 1 over sine of pi over 4 minus cotangent is the reciprocal of tangent. This is equal to c. Now, of course, in terms of both of these, sine of pi over 4, that's going to be 1 over square root of 2. So I'll just go ahead and note that here. So this is just 1 over square root of 2, or root 2 over 2 if you want to say that. Tangent of pi over 4, that is just 1. So with that, we know that c just ends up being pen is acting up again. So c just ends up being 1 over square root of 2, which is just square root of 2 minus 1. And so this is what our integration constant is. And so finally, our final answer will just be all of this, but c is just equal to square root of 2 minus 1. And so I'll go ahead and switch colors and write that in. So we have cosecant of x plus y minus cotangent of x plus y equals x plus square root of 2 minus 1. And that would be our final answer to this initial value problem.